Hello, Dynamic Planet. All right, this is my first video in a series dealing with earthquakes. We have a lot to cover, so let's get started. An earthquake is a sudden movement of the Earth's crust that's caused by the release of stress accumulated along some different things. We're mainly going to study things called geologic faults or plate boundaries. Okay, a fault is just a crack in a rock, or volcanoes, which we're not going to focus too much on, but they do happen. So why should I study earthquakes in the first place? Well, number one, eventually you're going to live in the real world and you're going to have to go to college or find a house, and you're probably not going to want to locate yourself in a place with a high amount of earthquakes like China or California. So it's just something to keep in mind, or if you do go there, then you have to educate yourself. Reason number two is obviously safety. How an earthquake actually originates its waves. Energy is stored because a force is applied to an elastic object, and that's called elastic potential energy. Potential energy comes in a variety of sources like mechanical, nuclear, chemical, okay, or elastic. Basically, if you pull something back like a spring, it's going to have some energy built up, and when you release it, that energy goes into motion, called kinetic energy. So the explanation for the sudden release of energy causing an earthquake is called the elastic rebound theory. And it kind of deals with the principle of elastic potential energy. This theory was discovered by H.F. Reed of Johns Hopkins, one of the schools I applied to. Sorry, H.F. Reed, no S. I don't know if you're going to need to know that name, but just in case, here it is. Okay, so here's the basics of elastic rebound theory. So we're going to monitor the progress of a fence, and we're going to say that there is some tension, there's some stress going along this plate and this plate that essentially causes some sort of a deformation. Okay, and that deformation causes the fence to bend a little bit. Eventually, the frictional forces get overcome, and it just shoots past each other in a vibrant shaking, which is what an earthquake is. And then afterwards, that earthquake stops, everything subsides, and the fences just naturally go in a different position. So if you see in textbooks, they might include a picture like this where a guy stands and takes a look at fences on different sides, and that's because the earthquake actually jumped past using elastic rebound theory. So the example I like to think of is snapping a stick or snapping a Kit Kat bar. Snapping a Kit Kat. Okay, so if you put a Kit Kat in the freezer, for example, or a fridge for a little bit, and you take it out, you put stress on it, which I guess I can include right here. You put stress on it on different ends, and it causes some deformation, so it bends until finally it starts snapping. The actual action of snapping is that rupture that we see with earthquakes, and then it finally just adjusts to its position. It's never going to want to go back to being a whole Kit Kat. It's now two pieces. So seismology. Okay, if you study earthquake waves, you're called a seismologist, and seismologists use a tool called a seismograph, and they want to read and measure earthquake waves. Okay, graph, that word or prefix or suffix, graph means to write. Okay, so that's exactly what it's doing. It's recording the waves. Okay, I'm going to show you how that's done in just a minute. The written record is called a seismogram. Okay, and there are two types of motions that a seismograph can produce, horizontal and vertical. So this one's a horizontal motion one, and I'm going to briefly discuss how these work. Okay, so you have some sort of an anchor right here holding this in place while a rotating drum spins around. Earthquake vibrations are going to cause this to move left and right, and that causes a seismogram to form right here. Okay, the opposite, or a vertical one is going to be held in place horizontally, or sometimes you'll see a cable right here, and this spring is going to go up and down, and that's going to cause some vertical seismograms. Okay, the location in the actual lithosphere where an earthquake originates from, that's called the focus. Where the earthquake starts is the focus, and we can classify earthquakes based on this focus, whether it's shallow, intermediate, and deep focus. And I don't think that you'll need to know this really, so I'm not going to spend too much time, but I believe shallow focus is less than 70 kilometers, intermediate 70 to 300, and deep focus is more than 300. Just for some reference there. The point on Earth's surface directly above the focus is the epicenter. And this is the most important part because when you're dealing with an earthquake, hey, there's this earthquake that happened 150 kilometers below Earth's surface. Yeah, I don't care. What am I what am I supposed to do with that information? No, but if you know the epicenter, we can track that over time. So where do earthquakes actually occur? Well, they occur in plate boundaries. They tend to happen at locations where plates of the lithosphere, they either converge, diverge, or slide against each other. If you remember, convergent means that they come together. So these plates come together. Divergent means they move apart. And if they slide past each other, that's actually a transform boundary. And in our tectonic plates unit, or whatever I teach that, I'm going to get way more in depth with this, but I just want you to have the general idea. So if you look at these two diagrams right here, you'll notice that these are all plates, like the Nazca plate, South American, okay, the African, they're all plates, and the actual lines where the boundaries occur go right along with this diagram that shows the major earthquake locations in the past few years or so. Okay, so they directly line up with the plate boundaries, right? Maybe not directly, but most of them do. Okay, so earthquakes, volcanoes, anything major that happens, okay, remember the event is called dynamic planet. Anything dynamic that happens is probably going to happen along a plate boundary. Okay, whenever two converging plates come together and one of them goes underneath the other one, that's called subduction. When two converging plates collide and one sinks because of a higher density. Okay, so let's say that I had a continental plate and an oceanic plate, and they're going into a wrestling match. And I want to know which one gets pinned under the other one. Well, you just look for the denser one. If you remember from chapter 1, continental crust is mostly granitic, which means that mostly made of granite, about 2.7 grams per cubic centimeter. Oceanic crust, the rocks that make up this crust are gabbro and basalt. That has a density of about 3.0 grams per cubic centimeter. So because oceanic crust is more dense, it's going to go underneath. Okay, which means that if you have a subduction zone that we're talking about, oceanic is going to be the one that we're going to focus on. So subduction zones also house seismic areas, not too often, but it does happen. So in this case, oceanic crust that goes underneath continental crust, you're going to have a line of earthquake spots, and those are called Benioff zones. And I have no idea how relevant this term is, but it's kind of obscure to me. Okay, you'll sometimes see this called Benioff-Wadati, and Wadati is just another scientist that came up with it, or another geologist, and Benioff is the main one. So if you're going to memorize something, memorize that. Let's talk about the actual waves that form, and you can kind of think of it as throwing a rock into a pond and watching all those ripples. However, they don't go in every single direction, they only go on the surface. Seismic waves go in all directions, especially the body waves, and when it originates from the focus, body waves are the first to get produced. So body waves travel through the earth and the inner parts. Okay, they are compressional in nature, which means kind of like a slinky. They have areas where they're really close together, and then they push other areas farther apart. They move back and forth like a slinky. Okay, so the types of body waves, or P and S waves, P waves or primary waves are fast, they occur first, they're powerful, they travel through all three states of matter, solids, liquids, and gases. So you can see right here it's compressional because you have areas of high compression, areas of not so high compression. S waves or secondary waves, okay, they occur second. Okay, they're slower than P waves and they produce something called shear stress. Shear stress is just the stress you get whenever you, cut a piece of paper. It's basically putting pressure or putting a force on a solid object because you see some sort of a deformation. That's why S waves don't occur in liquids and gases, because you really can't put pressure on them. You really can't deform a liquid or a gas, so they only travel through solids. Okay, so those are the two types of body waves, and as you can see right here, they normally go left and right, but they travel through the entire body of the Earth's interior. So here is a picture of body waves acting together, primary and secondary waves, kind of going up here to the house. Okay, so I said there are body and surface waves. Surface waves occur after body waves, and they travel through the Earth's crust. They're slower than body waves. But they are more devastating. They're more destructive because they occur on the surface, so they're the movement that basically terrorizes and is responsible for the collapse of buildings. I just want you to be familiar with the recognizing of the names or the types of surface waves, and that is Love and Rayleigh. I don't really care that you know what they look like, but if you do want to know, I have some excellent visuals on this website. The actual act of locating an earthquake is more complicated than people like to believe, but it operates on this principle. P waves travel faster than S waves, so there's a difference between the arrival times. It makes me think of the classic story of the tortoise and the hare. As you start the race, 1 second later, you might see a difference between the hare, because the hare is obviously going to shoot past the tortoise. Tortoise is slow. But after 5 seconds, there's a way bigger difference. Okay, so this difference is going to allow scientists or geologists or seismologists to compute exactly where the earthquake originated from. A higher distance means it started out farther. Because let's say I have an arrow right here, and we shoot them off different velocities. So I have arrow number 1, arrow number 2. Well, at the beginning, at maybe 1 second, as I've discussed right here, there's no real difference. There's a little bit, but after like 5 seconds, you're going to see a lot of difference. So you can track this distance to being traced back farther. So you can use this difference to calculate where an earthquake originated from by using published graphs. And I have published graphs right here that we're going to take a look at in just a little bit. But I want you to know that you do not have to know this. You do not have to have them on your reference sheet. In fact, they will give them to you if you ever need to answer a question on that. Okay, and you're going to use published graphs located on Google. Yeah, Google is actually a blank. Deal with it. When you know the location, or when you know the difference in P and S waves for 3 seismic stations, which I'm going to get into in just a second, you can actually calculate the location of the epicenter. The epicenter is just the surface version of the focus. And you do this in a process called triangulation. And let me talk about how you actually do this. So step 1 is to find the difference in arrival times for each station. So note that the earthquake actually didn't originate from any of these stations, but the same earthquake is measured in each of these stations at a different rate. Okay, so we tracked the difference between P and S waves for each of these 3 stations, and we noticed that each 3 of these stations have a certain distance to the epicenter. And you just go down to these graphs, you find the difference between P and S waves, and then you go down to your x-axis, and there should be an epicenter distance. Okay, so it's kind of proportional. So if there's a high amount of discrepancy between your P and S waves, if your S waves happened way after your P waves, well, that means the actual earthquake happened way farther away from the starting point of your seismic station. So San Francisco, for example, 300 kilometers. That means that the difference in P and S waves yielded on the graph an epicenter distance of 300 kilometers. Okay, well, the thing is, this is the seismic station. It's 300 kilometers in which direction? 300 kilometers here, 300 kilometers here. 300 represents the radius of a circle that you're going to draw using a compass. So you're going to do that for each station. Step 2, as I said before, you're going to use these differences to calculate the distance to the epicenter. And step 3 is to use a compass to actually draw these 3 circles in that represent the distance to the epicenter calculated using those tables on Google. So after you draw these 3 circles, the point of intersection, note the triangulation right here, the point at which all these intersect is the actual location of the epicenter, which is pretty cool. So here are your 2 tables, and I just want to talk about them briefly. If I had to guess at which table they would give you, it would be this one, because this one is kind of obscure. I didn't really find it that relevant. This one's more prevalent in textbooks, but I'm going to teach you how to read both nonetheless. You can see P wave occurred here, S wave occurred here, and you can manually calculate the difference. So I have some questions. Part A. Calculate the distance to the epicenter if a seismic station recorded a difference in P and S waves of about 6 minutes. Okay, what you're going to do is you're going to either go up to this graph or this graph, and you're going to find 6. Okay, remember the y-axis says difference in arrival time of P and S waves. So since that was 6, we're going to go over to where the graph is, and we're going to go straight down to the x-axis. Okay, so that looks like it's about 4,200 kilometers, which we can write as our answer. The alternative is if we know the difference is 6 minutes, It's glitching out on me. Okay, if we know the difference is 6 minutes, what we can do is we can kind of draw a line. Guess not. Guess not. All right, whatever. You draw some sort of a line that signifies 6 right here, and you find out where the difference is exactly equal to this line. So you're going to go up, and looks like I already drew the line. So that's a difference of about 6. And if you go all the way down to the x-axis, you'll see that it's still about 4,200 kilometers. Part B. If an epicenter is located 5,000 kilometers away from the seismic station and S waves arrived at 9:16 p.m., find the time of arrival for the P waves. Okay, so this is one where you cannot use this graph. It's not going to tell you P and S waves separately. So we know that the epicenter is located 5,000 kilometers away. So I'm going to go ahead and denote that. Okay, so 5,000 kilometers away is about right here. Okay, so the point at which P waves happened was here. S waves happened about right here. So P waves and S waves, you have to manually calculate the difference in times right here. So S waves, that looks to be about 14. P waves looks to be about 8. There's a time difference of 6 minutes. So here's what we know. We know the epicenter is 5,000 kilometers away. We use that to calculate that the difference in arrival time is 6 minutes, or it's about 6 minutes. The S waves arrived at 9:16 p.m. Well, we know that S waves travel slower than P waves, and they travel second. That's why they're called secondary waves. So P waves travel before then. And if there's a difference of 6 minutes, if S waves arrived at 9:16, P waves had to arrive 6 minutes before then, which would be 9:10 p.m. Okay, that's it for this lesson. The next lesson, I'm going to actually do an epicenter lab, hopefully, and we're going to take a look at how to actually calculate the epicenter of an earthquake using charts and graphs.